everybody. This morning I'm going to talk to you about transforming other content. Mostly, actually, what that means is taking other content and transforming it into FHIR format, or vice versa. Technically, actually, we're getting interested in more than that, but that's what we'll stick with. So in terms of this space, the current problems that we're going to be talking about, the most common is actually implementing FHIR as a facade on an existing data store. If you're going to do that, and that's how most people implement FHIR, then you actually have to write some code somewhere that maps from your existing store to the FHIR representation. And your code will have to be able to convert in both directions if you start doing right. Alternatively, you might be using some kind of an interface engine structure of some kind to convert from V2 or HSM V2 or CDA to FHIR or XDS or some sort of edifact message or some sort of fixed width or comma limited file. There's a huge variety there. Or you might be doing something quite different, which is converting specifications to FHIR profiles. You're not actually doing data at all. Just taking a set of ideas and converting them, transforming them into FHIR profiles. That might be openEHR archetypes or templates, there might be national specifications, whatever, just other standards. And finally, you might be converting from FHIR to a wide variety of outputs. Any of the stuff I've already mentioned could be output artifacts. And you could, and I thought I'd point this out while I was here, you can include supporting additional media types. So you could say, get me an appointment, but I want the appointment in an iCal format. Now, a couple of people asked me about this. We don't ever describe doing that with the service, with the RESTful API. But we don't say you can't, so you can. And so some servers routine, the public test servers routinely support text HTML, just as a user convenience for browsers, for developers. You go and you just type in the URL and you get back an HTML representation of the resource. And you didn't think about that, mostly you didn't think about that, but what actually happened was the accept type was text HTML, and so the server served it up. And so in the same way, the server can, you can just add more and more media types, and the server can just do an implicit conversion. We don't describe that, but that's kind of expected behaviour. It's not non-conform or anything. We just never seen the need to actually describe that. But a couple of people have been surprised about that, so I thought I'd point that out. So really, it's in the end, you're just transforming to other content. It's just a convenient way to invoke that. So the first place to start is understanding the problem. So you're going to start with some kind of byte format, a document format of some kind or other. And this might be XML or JSON or some arbitrary sequence of binary bytes or whatever. But in the end, it's a sequence of bytes in some kind of a file or a stream or a network connection of some kind or other. And logically, it represents some sort of tree of data that's some logical representation of those bytes. And mostly, we deal with the logical representation. Not always, but it's way easier to separate concerns out. Parse the binary form to some kind of intermediate object representation, and then perform actions on that object representation. And then, in almost every case, there's some class model or specification or content model that describes the logical model, the object model. And sometimes you're lucky and that's in UML, and more often you're not lucky and it's not even computable. But there's almost always some kind of content model for the content. And you can transform at any level. And actually, the first problem we're going to talk about is the bottom problem of transforming from source to from model to model. And you might hear the words model to model transform used. That's terrible. I think that's terribly misleading words, because if you follow what I've talked about here, a model to model transform is this bottom form here, transforming a model to a model. But mostly what they actually mean is running this middle transform here with a model driving the transform. So really it should be model-driven transform, but for some reason I have never defined, it's commonly called model-to-model transform, unless it means you're actually talking about something else again. But that's typically what it means. And you can do the top line if you sort of prefer brute force and total speed efficiency, and you're prepared to spend way more time doing the transform. You can do the transform byte to byte without going through some intermediate form. But I really very rarely see that. It's just not feasible. We will go for some intermediate object form and then do the transform object to object. Now, when it comes to actually doing the transforms, there's a profusion of choices that we have. And the most common choice by far is to just grab some general purpose programming language, some kind of 3GL, maybe a 4GL, and go at it with your object models. And write some procedural transform, and you might use Java or C# or JavaScript or any other language of your choice. Or you might not like programmers, and you might want to use XSLT and some kind of state-based transform engine, which I can't go past without saying XSLT makes my skin crawl because it's a state engine. Well, you might use XSLT because you're an XML kind of person. Or you might use any kind of specialist transform language or toolkit, and there's a heap of specialist transform languages, and MDMI is an OMG spec, which you might argue is a transform language, or a toolkit, or a bit of both. And there's all the interface engines include some kind of framework for doing these kind of transforms. And there's some specialist language like Tickle, although there's more than that. And then we went ahead and defined our own language for that, which we'll come back to, and whether that's a good idea or not. And when it comes to choosing an approach, I think there's some criteria to keep in mind. And people argue about the priority of these criteria, so I'm not in any particular order here, except I do think that the top one here is the most important. The most important thing about whatever you choose for your transforms and how you use the transform technology of your choice is that you have to have a clarity and traceability back to requirements so that people who maintain the transforms can understand what you are doing. Because I've never seen transforms that don't require significant amounts of maintenance on an ongoing basis. And if I go into any healthcare institution and talk to them about pain points, ongoing maintenance of transforms is not the words they use, but it's the facts they tell. And so there's a lot of technical debt in badly documented, badly organised transforms, and in particular, a lot of transform language toolkit approaches that come with interface engines. They've got this beautiful user interface that allows you to point and click, and it's really cool. It doesn't do the things you really need to do, and there's no way to good documentation and requirements traceability. And so I'm a programmer, so I strongly prefer some kind of language where I can comment and put requirements in. But the most important thing is always clarity and traceability. And you need to actually be able to express the transforms you need to make, and they can get pretty complicated. When we were working on the FHIR mapping language, Lloyd and I and a few others actually made a requirements list of abstract requirements for transform languages. And some of them are really simple. You need to be able to rename fields. Yeah, that's pretty obvious. But some of them, you need to be able to restructure trees so you move your cardinalities around, and you need to be able to do string-based transforms, and then there's states. And there's a whole bunch of, and then there's the ability to trade between different ways of referring to content in different frameworks. You know, there's URLs in the web framework, but other different frameworks have different ways of referring to content. And so there's a bunch of expressiveness requirements that you need to be able to implement, and some of them are pretty hard. And then you worry maybe about performance. I mean, You do worry about performance. If you're getting 2,000 messages a second coming through and you can transform 100 messages a second, well, you've got a problem. And sometimes you can parallelize it, and sometimes you can't. So performance really, you have to be able to perform. But if you're getting 4 or 5 messages a second, and you transform, you can say, oh, I could move my transform from taking 100 milliseconds down to 50 milliseconds, you're wasting your time, because you have capacity. And so you just have to be able to perform as quickly as you're receiving messages. And actually you need sort of a 10% space, but anyway. Then something that I think a lot of people don't really think about, and that's portability. If you're going to invest in a transform, and you're investing, as you should, in traceability and clarity, and then someone says, oh, that's a really good transform, can I run it somewhere else? And you go, oh, no, because you have to rewrite that somewhere else, because you can't have the same transform engine. And I'll come back to talking about portability a bit more later. Portability equals reuse, and equals the ability to leverage your content. And so I think that's much more important than most people actually, it deserves more investment than most people get. And finally, and I really think this is very much vital, I said they're not in order, but I really think this one comes at the bottom, is people will choose a language that they're used to, a transform language that they're used to working with. And so a lot of people who should know better, because they're programmers like me, just go ahead and fire up a Java class and away we go, without really thinking about these other criteria. And those can easily become, without strong discipline, very hard to do any traceability, and very hard to become portable. So those are the kind of things you need to think about as soon as you start thinking about transforms, and really, honestly, we live in a life where everything's a transform. I haven't taken portability now. So portability, you write a transform in your language of choice, and I don't know, maybe you write the code, a class that converts from a FHIR resource to your database, and vice versa. So that's really good. And if you're like any programmer I've ever worked with, it's really good to write, particularly in your code, it's really good to write that in a nice efficient class in your code, because you know what, you have this vast array of libraries and loaded infrastructure that you can just call, and that's really good. And then someone comes to you later and says, that's really good, can we write now a data extraction that uses the same logic to do a data extraction, so we can pull out a flat file in a background process? And you go, no, because all the code I wrote depends on being in the web server with all the loaded infrastructure that takes, 5 minutes to load, but runs in the background of the web server. That's not a portable transform. Or you might be a national program, and someone says, I wrote this transform that transforms from your standard X to last year's standard Y, and it's really good. I think we should just give it to everybody, and everybody else looks at it and goes, I can't run that transform, I don't support language X, I don't have the right infrastructure. So if you can have portable transforms, you can take the transform and run it somewhere else, then you can scale and you can invest more in the transforms, getting them right and getting them shareable. But we don't have a culture in healthcare of portable transforms. In fact, I should rephrase that. We don't have a culture in IT of portable transforms. And really, it's a bit astonishing, actually. So, and it's can you run the language? Is the runtime that you need to run the transform, whatever it is, portable? Okay, maybe everybody can run JavaScript, but can you run JavaScript at this point? In the right point in your application? Or certainly, it's written in .NET and you've got a Java stack. And the other thing is, does the system provide compatible services? And the thing about all these transforms is the transforms need services from a system that they run in. The transforms, to some degree, are not able to convert between literal references and loaded data structures. The system has to do that. And if you're taking a single package and converting that package of information to another package of information that's got the same scope, you're not going to break it up into pieces or combine pieces. You don't need to worry about this. But as soon as you get to like a moderately complicated transform, root world transform, you're going to have different scopes. You're going to take this package of X material becomes 25 things in my output stream. And to actually build 25 things, that's not something that a transform language can typically do by itself. You need to make assumptions about how that happens. About, am I running a file system? I can just create files, or do I have to have some kind of created object? You're talking about the system now. And if you're talking about portable transforms, you can actually think that process through and how to separate out your concerns, and so you can have some sort of service that the system provides that can do those things, and the transform can just assume they'll happen and become portable. And then the other great thing that comes up is persisting identifiers, identifying previously used identifiers, mapping from identifiers to identifiers, persistent services, and creating new identifiers. So those things, you need system support somehow. You can actually hard-code them in the transform, but what you've done is you've hard-coded system expectations, system assumptions into your transforms. And finally, you need some kind of terminology services. You can hard-code code-to-code transformations, but as that problem scales up and you start dealing with really big terminologies like Snowman and Link and so forth, you need terminology services support, and I'll talk a little bit about that shortly. And so I think not enough attention is paid to portability because it's about cost. And it's about current cost now versus cost in the future. If we invested in portable transforms, our cost in the future will be significantly reduced, but our cost now will be a little bit higher. And so, of course, given that choice, every business person I've ever met says, well, we'll have cheaper now, thanks very much. Cheaper in the future is someone else's problem. Okay, so let's go back to the problem now. When we talk about transforming content to content, you remember that almost always you've got some kind of underlying model. The content model, class diagram, schema, whatever you call it, you've got that. And you're going to map from one schema to another schema, model to model, whatever you call it. And when you map from content model to content model, there's basically 4 levels at which you can map and publish. So the first level of mapping is called skeletal. In the mapping, there's just enough information for a moderately competent reader to realise what your intent is. So you've gone through and said, well, these are the choice places in the mapping from version 2 to FHIR. And I'm going to tell you about the choices and figure that you can figure out the rest all by yourself. So that's a skeletal mapping. I'm just mapping out the skeleton of the classes. The next level is to step up and say, we're going to do notional mapping. We're going to go through all the class, all the elements, the attributes in the class model, and we're going to, for each of them, we're going to indicate which elements in the destination model correspond to this element. So you're saying this element are about the same thing. About the same thing is the important bit. The types might match, it might be an integer on one side, a string on the other, or some kind of coded thing that's not quite equivalent in the way it supports codes. And there might be all sorts of caveats and special assumptions, but at least anybody dealing with the content knows those two things are roughly the same concept. And then the next level, which we call conceptual, is that the concepts are fully mapped. And we've gone through and we've chased down all references and we've chased down to primitive attributes and mapped from primitive attribute to primitive attributes in all cases. And most people, when they do mapping between models, this is what they think they're doing. Sometimes it's not what they're actually doing, but it's what they think they're doing. And the thing to pay attention to here is that very often, even though the attributes are mapped, the primitive model, the primitive content, the primitive data types don't fully align from source to destination. And there's some values that could go in the source that don't fit into the destination. And so the value domains are not fully mapped, and there's some special cases, special exemptions that you haven't figured out how to handle, but you're still leaving it as an exercise to the reader to finish it off. And if you're sitting down to actually write the data transform, obviously the further down here you are, the better off. The better off you are, because someone else is eliminated as many special cases as they can, and you don't have to come up with very many. And then finally, there's what I call executional level of mappings, which is the mappings account for the full sets of value domains and all the attributes of all the content possible inputs. All the special cases are handled, and you've written down how to construct lists, which is almost always left as an exercise for the reader. So, and at that point, because you've talked about how to construct the right set of instances, not just how to map attributes, at that point you can feed that mapping into an engine, say, data in, valid data out. That's simple. So, obviously, each step down this cascade, there's an additional amount of work, probably an order of magnitude greater amount of work at each step of the path to walk down that cascade of levels of mapping. And it's really easy to think that you're doing conceptual mapping, but actually to be doing notional mapping. And it's really hard to do executional mapping. And in some cases, doing executional mappings becomes the actual conceptual mappings that are going on become so obscure because your mapping is so dominated by special cases that no one understands it anymore. And in fact, that's one of the fundamental challenges in transformation. The details obscure the concepts. Okay, so that's my framework for understanding mappings. So let's talk about FHIR. In FHIR we have a bunch of mappings. How many people have ever actually looked at the mappings tab of a resource? Not everybody. I encourage you to do this. And I've had a number of people come up to me and go, FHIR, you should really map from this to this. And I'm like, we did and it's published, have you ever looked? And they go, no. So look at the mappings tab for the data types and the resources. We put a lot of work into the mappings. So here's the mappings for version 2 patient. And you'll see that the mappings here are notional mappings. We mostly map things, but some of the mappings are pretty hand-wavy and they're not in any computable form. But if you read them, you kind of get emotionally these things are about the same things. We haven't mapped gender in version 2 is, well, it's a variable thing. Depends on which version you're using in version 2. We haven't done any of those things. We just said that the patient gender is PID8 in version 2. Right? That's a notional mapping. Here's a skeletal mapping out of the FHIR spec. Mappings for consent to financial consent in the RIM. And you can see that we've only mapped the choice points and we've just left it to you to figure out the rest. We're just telling you the things that you might stumble over. Or it could be that we're just being lazy at this point and we were going to eventually do notional mappings, but we haven't done them yet. Actually, probably the case in this case, but nevertheless, at this point, it's a skeletal mapping. We have some mappings in the FHIR spec that are nearly conceptual mappings. So this is Lloyd at work. I don't think Lloyd's in the room though, but this is Lloyd at work, and Lloyd and I collaborated on this. We've got the FHIR patient and the RIM patient class. We've gone through and you see the first few code mappings are actually pretty similar, although, you know, when it comes to actual status code is that's a Boolean and status code is code. So there's, you know, more mapping to be done there, but we figure that you can figure that out. But you can see once we get down to gender and birth date that we're actually starting to fill out some details about what the mapping is, starting to make it actually fairly precise. And Lloyd and I, when we started working on this, we had this sort of ambition that we could get this down to be authoritative and executable. But we can't, because there's too much variability. Even amongst a small community of people who've done version 3, there is too much variability for us to actually nail it down. There's no single authoritative transform. So you see, if you do look at the RIM, is there anybody in the room who would care about the RIM mappings? Yes. Oh, one. Alec, congratulations, Alec. There's not many. So it's not going to get much attention. But that's an example of nearly conceptual mappings, and there are some resources that are better mapped than others. We have other kinds of mappings in the spec. So more conceptual kind of mapping, notional kind of mappings, and this is an example. We've gone through and mapped for the patient patient elements to LOINC codes that could be equivalent observations. So that's the LOINC code for a patient birthday. And if you were living in a purely LOINC observables world, then we're giving you, well, enough information to pick up the patient birthday. You're on your own with everything else. And I do suspect that we could probably fill out some more columns here, more of these cells, but we haven't done so. I don't know what the thinking there is. We have got some executable mappings in one place. We've actually specified using RDF assertions of equivalence, the mapping between a FHIR coding and a RIM coding, a RIM CD. As you'll see, we actually, in order to get this to be actually authoritative and in RDF, the first thing we needed to do is to rewrite the RIM in RDF and actually change the RIM a bit in RDF. And there is nobody in the room who cares about that part. That was kind of a research project for Lord and I. And maybe one day we'll actually bring the RIM back as a pure ontology and see if we can get some more value out of it. But there's not a lot of energy for that. All right. So those are the mappings that we have, the range of mappings that we have in the FHIR spec. Now I want to talk about the FHIR spec itself, the support we have for transformation. So the first thing that we have is a concept map. The concept map defines relationships between concepts defined in code systems. In other words, if we were mapping from, say, LOINC to Snowman. And these kind of maps are pretty common, and in fact, there's not really sort of common specification for them, so we wrote one. And so you can use in a concept map a set of relationships between code systems. And the terminology server can execute a translate operation, so you can just say, hey, terminology server, I've got a Snowman code, can I have a LOINC code? And maybe you can, maybe you can't, but you can at least ask. And the terminology server process is starting to become really mature, and that's getting to be kind of useful. And then FHIR provides some concept maps, and we're currently talking about a procedure where HL7 can curate shared concept maps on behalf of the wider HL7 and FHIR community. So we can say, well, you know, almost everybody's going to need to translate between some common coding system and some other common coding system. We're all going to have to do it. Well, why don't we just share it through HL7? We don't have a framework for that, but there really seems to be no other authority to take that on, and so HL7 is talking about taking it on. The mappings I just showed you are all embedded in the profiles, and that's a reusable structure that everybody can use, and I want to have a quick look at that. And finally, we define a structure map resource, which is a language that defines transformation from one set of data to another set of data, a la my original description. And we provide libraries and servers to perform the translations, and in addition, we provide, in the specification, a fairly full set of R2 to R3 transforms backwards and forwards. So you can read the spec and they're executable transforms. So you can, if you ever wonder, how does this thing relate in release 2 and release 3, I can't figure it out, you can go and look at the transforms and find an automated transform that may explain how they relate. Although in some cases, I wrote them, it took me a month to write them, I'm looking at them going, I don't know how those things relate. The committee's sort of just changed their mind about this, and then I've gone to the committee, and the committee's going, yeah, well, we changed our mind. We never thought about how you would map data, because you can't. We just changed it. So the maps are incomplete in that respect. And here's a FHIR concept map. You start with a list of translations between a code system and a code system, the source and the target code systems. And they can have versions if you want. And then you specify multiple elements, a code in the source system, and one or more codes that it relates to in the target system. And then for each of those, you can define an equivalence, how they are related. And you can see the equivalence can be, these codes are related. We don't really know how they're related, but we know they're related somehow. And that's mostly what you get when you migrate old concept maps and people haven't really thought about they're related. They're just kind of related somehow. And then we can say, well, they're actually equivalent, or we can say we're really, really sure that they're totally equal, or we can say that they kind of overlap, or we can actually say, you know what, these are not the same thing. We want to tell you that these are disjoints. They are not related to each other. And so you can make a very long list of codes and transform table, and there's some quite long lists in the specification. And then you actually can, we'll come back to that one, you can actually execute this. You can say, hey, terminology server, given a composition status code of preliminary, can you tell me what that looks like in version 3 act status? And the terminology server will respond with, yeah, here's what it looks like in act status. It looks like active. So that's a really useful service to get, and you can delegate all of the hack work off to the terminology server and share, as a community, share concept maps. The really interesting thing about this is, what we say in FHIR is there's a bunch of implicit code systems in FHIR. How many people knew about implicit code systems? Yeah, oh, more than I thought, a few. So we actually say that every structure definition that you'll ever see, the ones we define, or profiles that are defined by nations, or projects, or whatever, is an implicit code system. The system URI is the canonical URL for the structure definition, and every snapshot element ID is an element, is a concept in the code system for that structure definition. If you're interested, this is a fragment snapshot of the specification on the concept map page. So you just go down and read the rest of the concept map page, you'll see this table. And the same for a questionnaire. You can go about the concepts in the questionnaire and map from questionnaire to questionnaire in some other format using a concept map. And also medication resources. Every medication resource I've ever seen has a corresponding code in the terminology. RxNorm or whatever, or DM plus D or whatever. Every medication resource has a matching code in the terminology. So you can actually use concept maps to map between concepts, and you can then start leveraging them for support. Also in profiles, we have mappings in profiles. So you start in the structure definition by saying this is something that we're mapped to. That's what we're going to use it internally identity. And this is its formal URI. And there's some more information about it. So we can say we're going to map from this, the content in the FHIR resource, we're going to map to content in some other specification. And then for each element you can say for this URI identified by linking the identities here, we have a mapping from, in some language which is often unspecified, from the content in the FHIR element described by the profile to some other specification. And all the stuff I already showed you that we have in the specification are done using this element definition mapping stuff. And this is what we have listed in the specification as mappings. We have LOINC, we have two kinds of SNOMED mappings. We have mapping V2, V3, DICOM, XDS, openEHR, and then we have CDIS, Quick, and you probably, I bet there's no one in the room who recognises every one of these. But we have all these, even double core, and committees just keep adding more and more, and that's fine. And in fact, it's a really good value proposition for all the consumers of the specification that we publish all these mappings, if only everybody would read them. Finally, we defined an actual mapping language. So this is a declarative mapping language that transforms data from one directed acyclic graph with metadata to another. So we say you're going to input, it's going to be, we're not interested in bytes, we operate at the object level. And you have a set of objects in some kind of a tree, and the objects will be marked up in a way that's available to the engine with a name, type, and cardinality. And so you can feed it one or more input trees, and you'll get back 0 or many output trees, and there's a system API that provides the kind of services I talked before to the engine, and the engine runs, and any transform expressed in this transform language can be run by any version of the engine that has that API from whatever system it's running. So we're talking about truly portable mapping transforms that can be just run across multiple systems. By the way, don't look outside, the sun's out. So the FHIR mapping language, it's not what I expected when we first started working on this. I ended up working with an author, author of the OMG model view transform, and the interaction between him and I had turned it into something very different to what I expected. I expected to get basically a procedural transform, that you would start with a set of data, and you would describe the methods that you would follow and under the conditions that you would follow them to produce the correct output. So very methodological, procedural-based transform. If you follow the method, then you get the right output. But Keith from MVT pushed me really hard on this, and we ended up defining a declarative transform. The declarative transform has no process associated with it. All you do is you specify the precise relationships and the conditions under which the relationships apply between the source and the destination. And then if you apply a standard method to those specified relationships, you will get the correct output, and you'll get that hopefully consistently and reliably correct. The really cool thing about a declarative transform as opposed to a methodological transform is that you can inspect the relationships and derive additional value out of the expressed relationships. And in particular, given an input specification and an output specification, given an input specification and a transform, you can actually construct the output profile. So, given that I know what's going in and I know what the transforms are, I can tell you what could come out. And I can describe the profile of what comes out. Or, given a profile in and a profile out and an express set of transforms, I can tell you if you're producing invalid output. It's a really cool thing to have that capability. So the mapping language that we define is purely declarative. It can apply to any content that is metadated directed acyclic graph, which automatically includes all FHIR resources and includes anything described by a FHIR logical model, which includes CDA in version 2, although I haven't looked at all of those yet, there's work to be done. But if you're prepared to code, then anything that you can code up to feed to the library with the appropriate API. And then you can transform between any content that's describable and any other with the language. And the cool thing, as I said, is you can inspect the maps and generate profiles and QA them. One thing to note is that we describe unidirectional mappings, source to destination. We don't describe bidirectional mappings. And the reason is because really, really simple mappings, you just flip the mapping over and you get the exact opposite. But as your mappings grow in complexity, it becomes increasingly difficult, particularly when you're restructuring content. You actually express the relationships differently and incompatibly. And also, very often, this is what you do. So I'm converting from some input format to some output format. I'm not concerned with the fact that I'm only ever going to use a subset of the output capability. I'm just going to tell you what I'm doing with the input capability. So when it comes to transforming the other way, there's a huge possible set of inputs that I won't be able to transform, but that's not what I'm doing. So you can flip the maps over programmatically, but the guard conditions to say when it's appropriate to use these, you haven't expressed them, so you have to fill them in. And Vadim here, hand up Vadim. Vadim's going to do a tutorial after morning tea on the mapping language, so I won't spend any more time on it because he'll do a great job. I do want to say that we've defined it, it's not comes naturally to people because it's purely declarative. That's hard work for you to think through how to make declarative mappings. But portable declarative mappings, pretty cool thing. And so you're investing now to benefit later. So it's worth looking at, but I'm not yet convinced that it has legs. But I'd like it to have legs. And it's up to the community. And I'll tell you finally, in a few minutes I have left, the big challenge, always the big challenge with transforms, is when you have missing information and you can't actually do the transform. And the most important and most common form of missing information is identifying the information itself. You don't have that, and so you're stuck. And so here's an example. On the right-hand side is the observation model from FHIR, and you'll see that the performer is a reference to a practitioner, and here on the left is a MSH, probably an OIU message, with an ABX, with a performer, Dr. David Docker. There you go, Dr. David Docker. That's all we know about the performer is his name. there's no identification on the record for the doctor. And we've got to convert that to FHIR. And you know, we could just fake up an identification for that. But when they send Dr. David Smith, is it the same doctor with a new name? Or is it a different doctor? Well, we don't know. So what do when we fake up the identification next time? Are we just going to give a new ID every time? Every time it's David Doctor or David Adam Doctor? You just don't know. And here's an equivalent in CDA. A CDA is fragment here. You see, the Substance Administration has an ID which is UID, an ID which is UID. And you go, well, I don't know what's the meaning of that UID. And so you go digging and you find out from the source guys who wrote the CDA document that every single object they create, they give it a new UID. They just create one on the fly every time because they've been told they've got to put IDs there so that we can persistently identify information. So what we'll do is we'll just make up an ID every time. That'll work. And then you can see they keep doing the same down here, everything's got an ID on it. And so you have an ID, but it's not actually the right ID, it's meaningless. And you might as well not have one. So what are you going to do about this? Well, sometimes you know because you've got, you know in your business context. And so a lot of transforms that we write, you can't finish them off because you don't know the business context. You don't know the institution running it, so you can't fill out the institution name first, for instance. So that's okay, you can manage that one way or another. The person who actually knows the business context can complete it. Sometimes you can fake up an ID with minimal damage to downstream business processes, like we just saw in the CDA document. Sometimes the damage to downstream processes is far from minimal. But what else are you going to do? Because in the end, if you can't produce a piece of mandatory information, then you can't actually do the process. And that's usually worse than breaking the process, is to break the process completely. There's no good answer to this. And that's much of the source of our trouble, is incomplete transforms. And it's also why, for instance, we allow stinking contained resources even though we hate them, because of this. And it's also why so few elements in FHIR have a minimum cardinality of 1. Because in spite of the fact that everybody consumes the information, would like them to have a minimum cardinality of 1, anybody who produces them would be stuck. Okay, and so there I am. I said questions and discussion, but I didn't leave you any time. I recommend the follow-up in this room, which is Simone talking about version 2 to FHIR transforms back, where she'll talk about some of this stuff, no doubt. And then Vadim talking about the mapping language. Thank you very much.